Fasten your seatbelts because we are going to do some serious math in this lecture. Okay, just kidding. You will learn about some basic algebraic structures that will come in handy later, especially for error handling and multithreading. An algebraic structure is a set with one or more operations defined on it that satisfies a list of axioms. Okay, imagine you are baking a cake. The ingredients are our set of things, and mixing two of them together is our operation. For our example, consider two things mixed together, for example sugar and flour, again as an ingredient. So our mix function has the following type. So we never get another type than ingredient, which is called closure. Not to be confused with the closures you know from lambda functions. Let's use infix notation for it. Mixing is commutative. That means that it doesn't matter if we first mix ingredient 1 with 2 and then with 3, or if we start with 2 and 3 and mix 1 with the result of the former step. So we have associativity here. Such a structure is called a semigroup. Do we also have commutativity here? Yes, because sugar mixed with flour is the same as flour mixed with sugar. And such a thing is called a commutative semigroup or abelian semigroup. What else can we think of that could be a commutative semigroup? Let's check natural numbers with addition. Closure, check. Associativity, check. Commutativity, check. So, numbers under addition form a commutative semigroup. But our structure has another property. There is a neutral element that fulfills the following rules. What is this neutral element? Of course it is 0. A semigroup that also has a neutral element is called a monoid. So numbers under addition form a commutative monoid. Can you think of a semigroup or a monoid that is non-commutative? Let's remember function composition. Take the following three unary functions as an example. They all have the same domain and codomain, meaning they have the same input type and output type. Such functions are sometimes called transformations. So composing two transformations results in another transformation of the same type. Closure is given. Function composition also is associative. But is it commutative? The types would match. But can we actually do this? No, of course not. For example, squaring a number and then doubling it is not the same thing as doubling it first and then squaring it. So composition is not commutative. So far we have a normal that means non-commutative semigroup. But is it also a monoid? Can you think of a neutral element regarding composition? A function that we can compose to other functions to fulfill the following rules? What would such a function look like? It would simply return the input without doing anything. So transformations under composition not only form a semigroup, but also a monoid. There are more algebraic structures like groups and rings, but we usually do not need these in functional programming. So let's keep it at that. Here is the whole thing in table form. More examples for semigroups are sets under the union operation, numbers under multiplication, and strings, or sequences in general, under concatenation. Here is an exercise for you. Can you find neutral elements to these three semigroups and thus make them monoids? Which of them are commutative and which are not?